ladies and gents, we are moving on to our optional module, and I chose for us graph theory and matrices. It's all fun, I love it. I can tell you matrices and graph theory, I would say matrices is very much for physics, so if you ever study physics, you will come across that a lot. Graph theory, I would say, is more for like computer science, and that's what we're going to start with. So a little bit of background about graph theory. You can look up, Google the bridges of Königsberg. Okay, that was when the first time mathematicians started thinking about that. They basically had a city with a river, or two rivers going over the city, and there were like 9 bridges or something like that. And this mathematician, if I'm not mistaken, was Euler. He was thinking, can you have a path that crosses all the bridges just once? Okay? That's the birth of graph theory. But honestly, now graph theory is super important. You might have heard this concept of big data. Okay? A lot of research in biology, in computer science, and everything, really, communication, involves taking a lot of numbers and crunching them together, finding an optimal solution. So you can say, let's say we want to put a network, 5G, okay? So we need a whole bunch of servers and then connect them with certain cables or whatever. And what would be the best setup to maximize the information speed and minimize the cost? So that sort of stuff is all about graph theory. So I've written a whole bunch of stuff that hopefully you came across last year. I think looking at the book, The Great 10, I think you probably did, but we'll just go through them very, very quickly. So what is graph theory? Basically, it's a theory that deals with two things, really: vertices and edges. Okay? So a vertex is like a little point, okay? And edge are lines that connect that point. Okay? So that is, for example, a graph. Okay? We have, we'll call them A, B, C, D, and E, and we have some kind of connection. Okay? Vertices and edges, the line that connect them. What could it be? It, for example, could be, I don't know, a friendship. It could be a friendship map. Okay, so D is friends with E, C, and A. A is also friend with B, and that's it. Okay, so there's friendship relationship between these five people. Okay, it could be distances. So that could be 5 different cities, and then this is an unweighted graph. That means there's no numbers, but I can introduce numbers. So this could be 20 kilometers, 10, 30, and 40. So it's like a map showing you the distance between the cities. I guess from here you can't go to them. Maybe there's no road. Okay. Sometime I haven't written it yet, but I might as well just do it there. We have directed and indirected graphs. So these are undirected graphs. That means you can go from B to A or A to B, doesn't matter. But sometimes you can have directed graphs where you specify specific direction, like a one-way system. Okay? So that's vertices, and edges. Oh, not really finished. So what you can't have in a graph, you cannot have, I'm just going to pause you here for a second. So it's important to also speak about what cannot be a graph. So you can, for example, you can't have a graph with just edges and no vertices. So there's no vertices there. That's not a graph. You also can't have a graph that, let's say, A, B, C, and carries on and on and on. You can't have infinite graphs. All our graphs that we deal with, anyway, are finite. And the last one is, you can't have, this is also not a graph, where you have vertices and edges, and then you have suddenly an edge that doesn't end up with a vertex. On each edge, we have to have 2 vertices. We can't have just edges that just hang up with nothing. Okay, so next thing we need to talk about is simple graph. Okay, just make some space. So what is simple graph? Okay, let's see what is not simple graph. So I can have a vertex or a graph like this, A, B, C. And I'll just do normal kind graph, and then I'm going to add multiple edge. That's a multiple edge. So from A to C, there's two edges I can go through. I can also add a loop. This is called a loop. That means it's an edge that's connected just to one vertex. Okay? So if you have loops and multiple edges, that is not a simple graph. Simple graph is one where there are no loops and there are no multiple edges. Okay? Let's move on. Okay, so that was simple graph. Next thing, I'm going to actually go to degree. So degree is, when we talk about degree, we talk about the degree of each vertex. So the degree of A is 1. The degree of C is 3. The degree of D is 3. The degree of B is 2. The degree of E is 1. You can probably guess that degree really means how many vertices, degree of a vertex is how many edges are coming out of it. Okay, how many edges are coming out of it. So, so for example, just to make things a little bit more complicated, let's say I add another loop here. So I've got a loop now. Now the degree is going to be 1, 2, 3. Okay, so a loop counted as 2 edges because, well, you've got 2 lines coming out of that vertex. So that's going to be 1 plus 2. That's the degree now is 3. So that's a degree. You can also talk then about a degree sequence. A degree sequence will be just listing all the degrees. So going alphabetically from A, B, C, D, E, I can write the degree sequence is 3, 2, 3, 3, and 1. That's the degree sequence. Okay? So what is now a regular graph? A regular graph is a graph where all the degrees are the same. The degrees of each vertex is the same. Okay? So obviously that is not a regular graph. But how can we regularize it? Okay, we'll add a few more edges. So let's try and get it all for 3. So this is 3, this is 3, this is 2. Okay, well, we'll add another one here. That's going to be now 3 as well. This one already 3. Now this is not 1, it's actually 2, but I need to add 1 more. So I'm a little bit struggling here. Okay. What I'll make up. I'll add another vertex. Okay, I'm making my life a bit easier. So that will be now F. Okay, so now he's got 3, the degree is 3, and I'm going to add another loop here, and then everyone is 3. Okay, so now it's a regular graph. Okay, I'll just pause here. Okay, it's all good, but actually what I just said now is not really right. Okay, so I can just tell you already that the graph theory is not a difficult part. It's actually easy. I would say probably easiest. The problem with it is there are a lot of stuff to remember. And so I can't really lie here. It's a lot of stuff to remember. So what I just said now is not really right, okay, about regular graph. Regular graph, yes, it is true that it has that all the vertices have to have the same degree. That is true, but that's not really the definition. Okay? So all the degrees here are really 3, but that doesn't make it a regular graph. A regular graph is a graph where all or each vertex is connected to the same number of vertices. So even though all the degrees here are 3, that doesn't mean that each vertex is connected to 3 vertices. For example, okay, vertex B is connected to C, D, and E, so it's connected to 3 vertices. Vertex F is really connected only to 1. Okay, so that's not a regular graph. Okay, an example of a regular graph, I'll go simple. Okay, that is, for example, a regular graph. Okay, so each vertex is connected to 1 vertex. Okay, if I add another one, that will be a regular graph with 3 vertices. Okay, I can also add, if I want to go, let's say, 4 vertices, so that could be also a regular graph. Each vertex is connected to vertices. Obviously, the degree of each vertex is also the same. But I can also add, for example, that. Okay? So if I've added these 2 edges, now each vertex is connected to 3 vertices. Okay? So that's still a regular graph. Okay? Now something that I know that some people get confused. These 2 lines, these 2 edges, they intersect. But it doesn't mean that they're not intersecting. You can't go from this edge to that edge. it looks maybe on the two-dimensional plane that they intersect, but it doesn't mean that they are connected, if that makes sense. If you want to think about 3D, then pull that line a little bit up, pull that line a little bit down, and they're not touching each other. But really, you don't have to think about it, because these lines don't have to be existing in space. They're just relationship. So this vertex is related to that, connected to that. This vertex connected to that. But these two edges are not connected to each other. That makes sense. Okay, so we've done regular, we've done degree. I think at this point I should go to complete. So a complete graph is a graph where okay, I'll just make some space first of all. Okay, a complete graph is a graph where each vertex is connected to all other vertices. So this is a complete graph with 4 vertices. So from here I can be connected to that, and to that. And that's true for all vertices. Obviously, every complete graph must be also regular by definition almost, right? Because if I'm connected, if the vertex is connected to all other vertices, that obviously I'm connected to the same number of vertices from each vertex. So it's going to be also a regular graph. But it doesn't mean that every regular graph is a complete graph. So this is, for example, a regular graph. Each vertex is connected to 2 vertices. Okay, so it's a regular graph, but it's not a complete graph. Okay, so maybe let's write it like that. If I have a complete graph, that is definitely also a regular graph. But the other way around does not really doesn't always, it's not true. So every regular graph is not definitely a complete graph. Okay, sometimes it is. This is a regular graph, which is also obviously a complete graph, but this is a regular graph, which is not a complete graph. How can we complete it? Well, we'll just add more vertices. So we're going to connect this one to here and there. Now he's connected to everyone. We're going to connect these two. So now this one's connected to everyone. This one I just need to add here, and he's connected. And now we've got a complete graph. Okay? So, complete. Let's make some space. Oops. Okay, our next little bit is complement, the complement graph. Let's look at this graph. We'll call that graph, we'll give it a name, A. Okay, so we made our 4 vertices, and these are the edges. Now, if I want to talk about the complement of A, or the inverse of A, we write it down as A with a line above. That's the inverse, the complement of A. Basically, it's going to be the graph with the same number of edges. Okay? Sorry, same number of vertices, but the edges that I'm going to use here are going to be the edges that I need to add to A to turn it into a complete graph. So what is the complete graph for these 4 vertices? How would I add it? So let's just draw the complete version. So the complete version is going to simply be all that, okay, plus that, and that. Right? I just need to connect the last few connections, so making sure that all vertices are connected. So your complement will just be what I had to add onto A to make it complete. So it's just going to be that, and that. Okay? This is A, this is the inverse or complement of A. Okay, pause here again. Right, so empty graph. Okay? What is an empty graph? I mean, just to understand it, it's basically a graph without any edges. So you've got vertices, but no edges. But the formal definition goes like this. Okay? If this is, let's draw our complete graph. So a complete graph with 4 vertices is only one away. It's like that. Okay? So we'll call that C for complete. Okay? So the empty graph with 4 vertices is basically the complement, the inverse of C. Think about it, okay? If this is C and it's a complete graph, okay? What is the inverse, so the complement of C? It's basically, okay, the graph or the edges I needed to add to C to make it complete. But if it's already complete, then I don't need to add any more edges. So it's going to be your empty graph. Okay? So we've got empty, think I can just put in connected as well. Okay, connected graph, and I'll erase that. A connected graph is one where there is a way to get from each vertex to any other vertex, not necessarily directly, but there are some, not a pattern, a sequence of edges that I can take. So right now, obviously, it's not connected. Okay? I'm going to start adding these. Okay? That's still not connected, right? So from here to there, or any of these vertices, I can't get there because there's no edge. But if I'm adding, for example, this one, okay? Just adding that little edge here. Now I can get from here, I can get to there. How would I go? I'll go from here to here to here to here to here. Remember, I can't just jump halfway through the edge, okay? These edges are not connected. It looks like they're touching each other, but they're not connected, okay? So that is a connected graph, okay? Now, I'll just pause here for a second. Okay, so I think at this point it's better we should talk about a bridge. So a bridge is an edge. You're not going to always have a bridge, but if you have an edge in a graph, that if you were to take it out, then it's not going to be connected anymore. The graph's not going to be connected. Then that is a bridge. Okay. What is the bridge here? So obviously it's this line. Okay, I'll draw it in green. Okay. So that is your bridge. If I was to take it out, then it ceases to be connected. Right now it's connected, but it relies only on that green edge. If I was to add one more edge, then that is not a bridge anymore. Because if I take it out, that's fine, I can go through this way. So you don't always have a bridge. Okay, our last bit is isomorphic, and yeah, I need to clear some space for that. Okay, isomorphic. I think isomorphic is probably the hardest bit in whatever I spoke to until now. Isomorphic. Iso means the same, morphic movement. Okay? So isomorphic graphs are ones that if you are allowed, if you shift, if you move the vertices a bit, you move the edges a little bit, if you manage to get from one graph to the other without cutting any edge, without adding more edges or adding more take away vertices, they are isomorphic. So let's look at these two graphs. Okay, right now they're not isomorphic because one way to know that graphs are not isomorphic, and that's probably one methodical way of doing it, is write down the degree for each of the vertices. So I've got 2, 2, 2, 2. Here I'm going to write 2, 2, 1, and 1. If the degree sequence is not the same, then obviously it can't be isomorphic. Okay? But if I want to make them isomorphic, what I can do, I can just add another edge here. Right now, these degrees are going to be 2 and 2. Okay? And this is the hard bit. In your mind, what you need to try and see is that how you can morph. That's the word, morph. Okay? This graph into this graph. You can morph it, isn't it? You just straighten this, okay? Right? You pull that one, sorry, you pull this vertex to here, put them all on the line, okay? And that's still going to be connected to that and that. So you can definitely morph this graph into that graph without cutting any edges, without adding any edges, vertices the same, okay? So let's just put a few more examples and discuss isomorphism. Okay, so a couple of graphs. We need to decide are they isomorphic or not. So let's look at these two. Okay? These two, they look quite different. But if you think about it, there's a lot of mental kind of imagining. Yeah? Take this little vertex, pull it over to here. Still connecting to these two vertices. What you will get is like a mirror image of this graph. Okay? You'll get something. If I move that one to here, I'll get something like this. Right, so if I pull in here, I'm going to get something like this. Right? Now that is not the same as that, but it's actually really similar. All I need to do is just flip it around, and then I've got that. So these are isomorphic. And they're definitely isomorphic. You can also, just to be on the safe side, maybe as a starting point, just count. Okay? Write down all the degrees. 2, 2, 2, 2. It's going to be the same here. So maybe that's the first thing you can do. Just write down all the degrees. If you get the same number of degrees for each of the vertices, then you can try and imagine. So let's do the same here, okay? So we've got 3, 3, 3, 3, and 4. Okay? These two look very, very different. Okay? 3, 3, 3, 3, 4. So we've got the same number of vertices, obviously. If you don't have the same number of vertices, there's nothing to talk about. It's definitely not isomorphic. Okay? So maybe that's the first thing to check, to see if there's the same number of vertices and edges. Okay? But then you can check the degrees. Okay? The degree sequence seems to be the same. Now, check this. If you pull that little vertex and just keep all the edges, all these other vertices are connected to it, and put it in the middle, you got that. So this is also isomorphic. Okay, let's look at some more. Okay, so here I've got a couple of examples of non-isomorphic graphs. Okay, looking at those two. Okay, if I count the number of vertices the same, 4, 4. If I count the number of edges, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. I've added another, did I add? Yeah. I think I added another, so that's definitely not isomorphic. But I think the most obvious, or you can also check degrees, so 3, 2, 2, 3. This one is 2, 3, 2, and now this is 1, 2, 3, 4. So there's one vertex with a degree of 4, so definitely not isomorphic. But I think the most obvious difference is the loop. Okay? If I've got a loop here, not there, then you're going to have to cut it. You can't morph a loop to become suddenly not a loop. Okay? Over here, okay, let's write down degrees. 1, 2, 2, 1. Here I've got 2, 2, 2, and 2. So obviously it's not isomorphic. There's no way for me to move these edges somehow and vertices and suddenly can make more connections. So these are not isomorphic. Right, that was a little introduction. Our next video is going to be mainly about the lessons